My name is Hendrik Ulbricht. I'm the chair of the afternoon session. Before we start with the talks, there's one thing which is close to my heart, and I wanted to say this. So I'm an experimentalist, and I do these experiments to generate the superposition states and ask the question, so how massive can you make these things that you still see superpositions? And if you have a cat at home, yeah, or your neighbor has a cat, yeah, please don't start experimenting. Yeah? It's unlikely that you can solve this problem. Okay, so now we have our first speaker in the afternoon, which is Richard Dawid from Stockholm University, and he will talk about who am I in the multiverse.
Thank you very much. Yes, it's a pleasure to be here and to start this afternoon session. I think I can jump right into my talk because in the morning the first several slides have been covered in an excellent way already. So I want to start right away with many worlds, which is going to be the topic of my talk. And just to recapitulate what has been said already in the morning, the canonical interpretation of quantum mechanics assumes this weird kind of two-level structure. On the one hand, the wave function and the equation that characterizes the evolution of the wave function, the Schrödinger equation. And on the other hand, this strange thing, the collapse of the wave function. And the reason why people for a long time thought that it is necessary to introduce that collapse had to do with this understanding that quantum mechanics, in quantum mechanics, the wave function after a quantum decision evolves into a superposition of different states. So, and the idea was, well, we don't observe those different states, so something has to happen in order to single out one of those states and turn that state into reality. In 1957, and as we have heard after similar thoughts by Schrödinger already a little earlier, Hugh Everett suggested that we may not need that collapse concept at all. And the way this reasoning goes is that if you start with a scenario where we have an environment, let's say, so an observer, and a quantum measurement, let's talk about a quantum decision, a quantum coin flip, let's say, that either ends up being measured as up or being measured as down by an agent. The problem was seen that, okay, the wave function characterizes the superposition of states, but we don't observe them. Now, it turns out that something that was later called decoherence happens if you just look at the overall wave function of that system that includes the quantum system and the observer and the environment, so everything is characterized by one overall wave function. And we asked the question, so if we characterize this entire system by a wave function, what happens if we have this wave function evolve? And we have this quantum decision and the superposition of those two states. And what happens is that there will be lots of interaction going on, so to say, in the evolution of that wave function. And this has the result that after a fairly short period of time, we will have two fairly separate, one may say, branches of the wave function that are in their future development fairly independent of the other branch. So what happens is that if we neglect very small interaction effects, let's say, or very, very small effects of the one branch onto the other in the dynamics, we can just look at one branch and take that branch as the entire system. and we won't make a huge mistake. We will make a very small mistake, actually, by doing that. So that means that if we look at the situation now in terms of observers, we can reasonably understand the observer to split as well into those two branches. So there is a fairly independent observer in branch up and in branch down, and to that observer, actually the world will appear as if there has been one specific outcome of the experiment, either an up outcome or a down outcome. So this phenomenon of decoherence removes one of the main reasons to think that there should be a collapse. Now, at this point, it may make sense to characterize the current state of that idea. So the idea initially was not very popular. It was only picked up much later in the 70s and 80s. However, it has become really popular today. And today it's one of the most discussed understandings of quantum mechanics. There are many different ways to understand the details, but many observers of the discussion in quantum mechanics believe that there is something to this idea that we should do without the collapse of the wave function. There are those who say that actually we do have a full-fledged model. There are others who say that we don't seem to have a full-fledged model because every individual way of spelling out the details has its own problems. And of course, then there are those who don't like the entire approach because of this, let's say, fairly counterintuitive understanding that all those different branches of the wave function are somewhat there, whether real or whatever. And also for the reason that some think that the problems the approach faces cannot be solved. So there are those three positions. I would myself think that I am in the middle position. I have worries about the idea, but I think that the basic argument is quite intriguing. So what is the core problem of this idea once one has understood the role of decoherence that removes some of the apparent problems? The core problem is how to understand probability. And if we look at the way one would understand probability in a collapse model, the way probability is understood is fairly straightforward. So before the measurements, probabilities of the outcome of the measurements are somehow encoded in the wave function. So the absolute square of the wave function corresponds to probabilities of the measurement outcome. Now, if we perform the measurement, let's say if we perform many measurements of a given type, we expect that the outcome ratio will converge to the probability structure that is implied by the wave function. That's what we have seen this morning already in a very nice way. Now, if that fails, this means that the theory is refuted. So the idea is that there is a kind of a disposition for measurement outcomes that is encoded in the wave function, and the frequency's view on establishing the empirical relevance of the probabilistic claims. Now, there are problems with this. There's a question whether we have frequencies with respect in cosmology, what happens with respect to the wave function of the universe. There are some other problems of that approach, but that's the idea how one should understand probability in principle. Now, the question is, if all of those outcomes are there after the quantum process, how come that we can still observe a probabilistic pattern of the outcome? How can we understand probabilities? And while at first glance that may be strange or may appear strange, there is actually a perfectly viable candidate for doing that, which is self-locating uncertainty. And the best way to understand self-locating uncertainty is in a completely classical example, and this is not a very specific example, self-locating uncertainty happens all the time. So it is one way we use probabilities. And the idea is, in this example, is that there is someone who tries to trace his or her ancestors. So there is one ancestor that is known to be the first for some reason. Maybe it's the first who took the name, and there is only one. The name was given just once, so you know that that's the root of all people who have that surname. And then you can trace from that ancestor downwards. The ancestor had two sons, and each of those sons had descendants. One of them had 10 descendants, and the other had 100. And then there is a fog. Then we cannot follow it anymore. And then we have all those people who carry that surname today, and we assume that all of those can be traced back to the ancestor. So the question is, do I have a basis for understanding how probable it is with respect to subjective probability, so how probable I should take it to be, that I'm the ancestor, I'm descendant of A, or I'm descendant of B. And what I do in order to understand this is I assess the self-locating uncertainty. So I know that all those lines of ancestry down to today are there. So it's not a question of whether they are there or not. The question is on which of those paths I find myself. And on that basis, assessing that probability, it's perfectly respectable and rational to understand that my ancestor is A, is B with a higher probability than A based on what I know about that system. Based on the fact that I know that there are 10 paths going down from one and 100 paths going down from the other. So that's the basic idea. Now, I could, in principle, try to apply this straightforwardly to the Everettian system. So now we have here this very nice branching structure, and I will assume for a start that all possible outcomes of a measurement have the same probability once there is a measurement. And second, that measurements can be distinguished from each other. So those are assumptions that will turn out not to be adequate, but we want to make them at this point in order to understand the overall structure of the reasoning. So we have this quantum flip, and we have up and down, and then we have a second decision and a third decision. So in such a system, I can apply safe location uncertainty and the principle of indifference. So I assume that it's equally probable to find myself in any of those branches at the third generation, once I know that I'm in the third generation. So I can extract the probability for being in a 3-up branch, or for being in a 2-up, 1-down branch, or anything of that kind. And I can do that perfectly well based on self-locating uncertainty. Now, things are not that easy, however, and I can understand that they are not that easy even with sticking to those two assumptions. For example, I can assume that there is another forking off in one of the branches, but not in the other. So what do I do with this? If I would do straightforward branch counting in such a scenario, I would end up with a 2-to-1. I would end up counting each of the branches, so to say, with the same weight, as inducing the same probability. And that clearly is not in agreement with quantum mechanics, because quantum mechanics will tell me that I have a 50% probability of the upper branch, and then if there is additional splitting, I will have 25% for branches 2 and 3. So this straightforward approach runs into problems, and I might try to make up my mind how I solve this. However, before I'm getting into this too strongly, it turns out that this is the start of a much more general problem, which is that in actual quantum mechanics, neither A1 nor A2 is actually fulfilled. So, of course, I will have different probability. I can have different probabilities of quantum outcomes. And in addition, I will not always be able to distinguish, to decide whether I'm talking about one quantum decision or about several quantum decisions. The reason being that the separation of branches relies on decoherence, and decoherence is a gradual process. So it's a matter of definition at what stage I decide to call this an individual branch and treat it as an individual branch. And there may be cases where that's not at all clear. So I don't have a clear, cogent algorithm to decide how many branches there are, how many decisions are in a system, and how many branches there are in a system at a certain time. So this means that branch counting just doesn't work. So the idea seems that there is one natural way, very generic way of understanding probabilities that would also apply to a branching structure in principle, but it does not apply, at any rate, it does not apply in any straightforward way to the context of many-world quantum mechanics. So what can we do? Everettian quantum mechanics, therefore, seems to be in need of another explanation of the Bohr rule, and the question is whether that can still be based on self-location or not. In principle, let's say there are several options, but I want to highlight two of those options. The first would be that I kind of impose the connection between the weight of the wave function. So let's say the number, the square root of the number that ends up being the probability in a collapse model, and should also end up being the probability in our case. I can say that I just posit that this is still the case. I posit that if I do a quantum experiment, that's going to be the case. So weights of quantum weights are crucial for understanding the probability structure, just because they are. I don't say much more about it, I just say that this is the case. And this actually was Everett's initial understanding of the situation. It is a natural perspective if one thinks about quantum mechanics in an instrumentalist way. So we have already heard about the distinction between instrumentalist and realist understanding of quantum mechanics. If I don't want to suggest that those branches are actually real, I only want to say that this is a scheme that can extract the outcomes of quantum mechanic experiments, it's no problem for me to say, okay, and this is consistent, and in addition, I say that quantum outcomes of quantum mechanics will be according to the Bohr rule. And that's all there is. So the question is should this be called an exemplification of general self-location on those branches? And I would argue that it's not very plausible to say so, because the attribution of probability comes from the outside. It works on the model rather than being part of the model, which means that it is an instrumentalist perspective that does not really suggest an interpretation in terms of self-location. The other alternative is to try to establish the Bohr rule based on requirements of consistency with respect to the assessment of probability from the perspective of an individual agent. So the idea there is that I look at an individual agent at one of the branches in this overall branching structure, and I ask the question, okay, so the individual agent now deals with this. The individual agent thinks that Everettian quantum mechanics is true, and the individual agent tries to understand how to extract probabilities from that. And the idea is maybe we can find criteria of rationality that sufficiently constrain the options that agent has in order to enforce the Born rule. And one line of reasoning in that direction has been initially suggested by David Deutsch and then developed further by David Wallace. And that was based on the idea of consistent betting on outcomes of quantum experiments. So the understanding was that if an agent bets on the outcomes of a quantum experiment based on the assumption that Everett quantum mechanics is right, how can that agent do that in a consistent way? And they spell out conditions of rationality, of course. And one crucial issue about this, and one that has been heavily debated, is whether those conditions are plausible. For example, one condition that does a lot of work is the principle of diachronic consistency. So the idea that if the person bets on that basis, it shouldn't be relevant. If the person bets on the quantum outcome, it shouldn't be relevant whether the branching structure much later in the evolution of the quantum system is one way or the other. So I don't want to have to wait until the end of time in order to make up my mind about branching structures. I want to look at the system within a certain time horizon, let's say, and already understand the probabilities, and they shouldn't change if anything in the further evolution changes. Now, and a number of other conditions, and they argue that if you apply those conditions, the only consistent way of betting behavior is betting according to the Born rule. So this means that the Born rule is established based on the requirement of betting for an individual agent on one of those branches. It is not established at the level of characterizing the model itself. So there are no probabilities with respect to branches that can be attributed to individual branches based on the Everettian model of quantum mechanics itself, but they only emerge once one discusses the betting behavior of an individual agent. So it seems that this is not generally self-locating either, because the rationality of selecting a betting strategy from an agent's perspective is decoupled from the question where the agent actually sits in the manifold's structure. So it is an approach that kind of distinguishes those two questions and treats them separately. More recently, a second suggestion has been made in the same way. It's also a suggestion that suggests that should be a unique, consistent probabilistic analysis from the perspective of an agent. However, in this case, the suggestion is, it's a suggestion by Siebens and Carroll being a cosmologist, a well-known cosmologist actually. The idea is that this should be based on self-location. So the idea is that if you look at a strategy of self-locating in the multiverse and applying criteria of rationality, then you get a unique strategy of doing so, and this strategy actually turns out to be according to the Born rule. So one important element in this kind of reasoning is what they call epistemic separability. This shouldn't be a separate bullet point, the second one, but an explanation, which means that the outcomes of measurements in the local subsystems are not affected by the environment, that shouldn't play a role for that specific process. Now, of course, here the issue arises whether there should at all be a probabilistic self-location of an agent that is consistent and that works if there is no non-centered foundation for probabilistic analysis. So if the model itself, the branching structure itself, does not give us the basis for self-locating, is it justified to expect that an agent will be able to do that self-location nevertheless, based on the fact that there is only one consistent way of doing it? That's I would think, not clear and has to be discussed. However, there are advantages to that position compared to the Deutsch models position, one may say. One advantage is that it stays closer to what happens in the classical limit. It tries to stick to the understanding that, that grasping probabilities in this context has something to do with self-location, generally to do with self-location. And it's also connected, which is, of course, it has a common root with the first point. It is conceptually connected to the statistical analysis of the cosmological multiverse. And that's why Carroll is interested in it. So let me just say very few words about that, because it also opens up another dimension of this many worlds discussion. There is also the concept of a multiverse, the concept of many worlds in a sense, also plays a role in modern theories of eternal inflation. If we have eternal inflation plus string theory in particular, then we will have many universes with different physical constants that emerge from the inflationary background. So I don't have the time to say anything more about that. The story just is that there is one causally connected overall physical system, let's say, and in that system we have a very, very fast expanding the background of the universe. And by phase transition in that fast expanding background, individual universes emerge which have which resemble to a certain extent the universe we live in. However, they can have different parameter values for basically all the parameter values that characterize an individual world. And this is very interesting and very important in understanding the parameter values of the physics we have, because one can use it for anthropic explanation of fine-tuned parameter values. For example, of the fine-tuning, or in particular of the fine-tuning of the cosmological constant. So one can say, if this kind of analysis, if this kind of theories predicts that among those many universes there are some that have a fine-tuned cosmological constant, and if I can argue that this fine-tuning is necessary for life, I can explain the fact that we are living in a universe with a fine-tuned cosmological constant, because first, physics explains that it predicts that it will exist, and second, the anthropic argument tells us that we can only live in one of those universes. So it's not surprising that we live in a universe where this is the case. Now, there are also difficult issues regarding the statistical treatment of the individual in such a context. However, it's clear that analysis of, for example, anthropic reasoning in such a context must be based on self-location of the individual in this set of universes. So if, as Stevens and Carroll suggest, something similar also happens in the context of the many-world theory, this brings those two contexts where many worlds play a role closer together. And that may be one interesting aspect of this. Now, 5 minutes? Okay. So I want to spend the last 5 minutes to address one additional issue that makes this already confusing story even more difficult. That's the issue of the mental. It was suggested very early on that quantum mechanics opened up new issues regarding the relation between physical and the mental. In the collapse context, there were some physicists like Pauli and Wigner, for example, who thought about the idea that the interface between the physical and the mental might be triggered, might trigger the collapse of the wave function. So they argued that it might be necessary to understand this interface in order to understand quantum mechanics, actually. And if we look at Everettian quantum mechanics, the relation between branches and mentality is an additional issue that comes up. And it was, for example, two different basic options can be distinguished here. One may think that there are many physical worlds, however, there is just one mentality. So to say one of those worlds is charged by mentality, which would mean that there is something like a collapse at the mental level going on, which is a fairly strange idea because it means that many worlds with zombie agents are conjectured. So they are agents that may act like people, but they aren't, and there is only one line of mentality that runs through this entire system. So it's uncomfortably non-physicalist. The alternative is that there are many physical worlds and there are also many minds. So there is no collapse at any level. One may still argue, and it has been argued, that mentality still selects the separation, the basis vectors of quantum mechanics. So it selects what we understand as individual branches in this branching structure, based on the understanding that we don't observe superpositions of states. So this discussion about mentality in this context once again opens up the discussion of whether one should have an instrumentalist or a realist understanding of quantum mechanics. And we already heard about the distinction with respect to realism, with respect to many worlds. We would say either we understand Everettian quantum mechanics to suggest that the real existence of those other worlds, or we understand this as a scheme that allows us to extract results of quantum experiments. Now, initially, many quantum physicists took the canonical interpretation to suggest an instrumentalist view on physics, and Everett himself actually also suggested an instrumentalist view on the many worlds quantum mechanics. However, lately, many worlds have more often been understood from a realist perspective. Now, the issue of mentality complicates this picture because there seems to be no instrumentalist way of positing other minds. If I understand instrumentalism in the sense of suggesting a genuinely physical picture as opposed to my mentality and my observations, the observations I make, it doesn't make much sense, or it's very unclear what it would mean to argue that, okay, but there are other, instrumentalistically, there are other minds nevertheless. So it seems that many worlds, in terms of many minds, clearly suggest a realist reading. And actually it was also understood by Albert et al. When they suggested that position in that way. Now, this means that whether or not one adopts a many minds hypothesis seems intricately connected to understanding the collapse issue. So there is a single mind Everettian quantum mechanics, for example, that kind of offers an explanation of the collapse based on the mental level. There is a many minds interpretation that suggests that one would want to have a deeper understanding of how probability is related to the wave function. There is agnosticism that cannot tell between the two. So there are all those positions, and they are kind of, in a complicated way, they relate assumptions with respect to mentality to attempts to understand the physics. So instrumentalist and realist readings are not anymore just philosophical meta-issues, but they have import, or they seem to have import, for the theory's consistency. So the question is, what does this mean for physics? And so I come to the conclusion. So it seems that those additional levels that I've opened up here, the level of the issue of self-localization and the issue of the mental, they open up different dimensions of discussing the physical content of the theory that are more closely related to quite genuinely philosophical issues. Issues of the self, of identifying the individual, issues of the mental. And it's not clear, I think, whether this is a characteristic of the current state, whether one should call that a problem for the current state of those approaches, or whether it indicates a long-term shift in the character of physics. And that may be to be seen. Thank you.
Thanks a lot for this lecture. I know this is up for question. Okay, so
I'd like to ask a question about self-location as the basis for the probabilities of quantum mechanics. Consider radiometric dating of ancient rocks, which depends upon the decays having been dependent on quantum decay probabilities, way before there were any cells around to think about self-location. It seems that self is quite irrelevant to Cambrian rocks.
So what you're asking is, in effect, a Schrödinger cat question, right? The question is, so we observe this now, so we do observe it. However, this went on for a very long time without observation, so let's say in a subsystem. And the answer would be, from an Everettian perspective, that the decoherence is happening already then, right? So it is. So this in this subsystem, those different branches can already be identified at that point. And once an observer enters the picture, the observer turns into an element of each of those different branches. So the overall system then is in each case is the system of the observer and the phenomena the observer observes.
Into all this stuff that happened in the early
well, no, from the perspective of the many worlds of the many world system, the decoherence happens whether or not there is an observer. The decoherence, that's
it seems to me there's two areas going on in the theory community that I'm not sure I picked up whether you have understood those differences, and I was wondering if you'd comment upon them. I mean, one of them is this idea of sort of what I would call an immediate many worlds theory, where if I make a measurement of a spin system tomorrow, it splits the universe into one case where I measured it up and one case where I measured it down. The other case, which I think is the one that many theorists are advocating, goes way back to the beginning of the universe with inflation, and that the sort of multiverse exists at this very special time, and that this is when we get some sort of many world interpretation. But that doesn't necessarily. I guess I want to ask you to comment on this.
Right. So the conceptual background for those two developments of many of those structures is very different. Right? So in the case of Everettian quantum mechanics, it is an interpretation of quantum mechanics, while in the case of eternal inflation, it is a result of a specific understanding of the evolution of the universe. So in eternal inflation, the reason why one posits those or comes to the conclusion that those many universes exist is that one infers from observations about the world we live in that the world should have an inflationary phase. That's the first step. So it has this fast expanding phase. And then the question is, what is a plausible physical concept that can explain the transition from that phase to a world of the kind we are living in? And then it is suggested that actually those explanations of that kind tend not to suggest that the entire inflationary background changes into a universe of our type, but there are nuclei of other phases in that background. And so there will be phase transitions into, so to say, normal universes, time and again on that background. And that creates those different universes. So the way of reason is completely different. However, it is also striking that there are some similarities, and there are actually people speculating about the meaning of those similarities, whether there are closer similarities than what one would assume at first glance. But conceptually, initially, they are very different.
Next, Mr. Rostis.
I would like to propose a test for the many worlds theory, so you can tell me what's wrong with it. You have a system in a pure state, and you divide it into two parts. One part is 99.99% detecting it, and there's just one outcome. The other part, you arrange for it to spread out, and then you direct it, let's say, at a photographic plate that has vast number, 10 to the 9 or something, molecules. So there's a very, very remote probability, according to orthodox quantum theory, that will be the outcome. According to the many worlds theory, all the outcomes occur. There are vastly many more outcomes in wildly improbable outcomes. And so you're almost bound to get, according to the many worlds theory, the wildly improbable outcomes.
Well, that
if we actually did the experiment,
so the result you're the result you're suggesting would be the result if you would apply straightforward branch counting. So if you think that the number of branches that are generated in such an experiment represents can be the basis for a probabilistic assessment, then that would be the case. However, everyone knows, of course, that this is not the case. So the question, as I discussed, the crucial question for understanding Everettian quantum mechanics is to understand why or on what basis Everettian quantum mechanics actually can reproduce the Born rule. So can reproduce the situation that probabilities of outcomes of quantum experiments are just like in canonical quantum mechanics. Now, having said that, it is a fact that Everettian quantum mechanics is not exactly equivalent to canonical quantum mechanics because there are very small effects of recoherence. So the possibility that those different branches influence each other is not zero. It's not exactly zero. It's very small, but it's not exactly zero. And the idea would be, and actually that was one of Everett's ideas, that one could distinguish empirically Everettian quantum mechanics from canonical quantum mechanics by measuring those recoherence effects. So there can be, in principle, there can be empirical distinction. Yeah.
Okay, so next question.
Hi, yeah, I wonder if you could quickly clarify something. I didn't quite catch it. You said something about an absence of a non-centered foundation of probability or something. On your slide it had something about absence of a non-centered foundation of probabilistic model or something?
Non-centered, yeah.
Do you remember? And I wondered, could you just say a little bit about what you meant by that? Didn't quite understand it.
So, yes, I used the term and didn't explain it actually. The idea is that one can ask two different kinds of questions about the universe. I can ask a question about how is the universe to me, so to say, from my perspective, and I can ask the question, so what is the universe like? And the idea would be, let's say the traditional understanding is that I can have a model of the universe that does not depend on my perspective, and and I can extract predictions from that model. Now, if that's not the case, if all I have is assessments from my perspective of probabilistic outcomes, for example, the question is how far is it legitimate to address issues that are normally attributed to a non-centered analysis, which, for example, self-location may be said is usually based on the probabilistic structure of the system itself, without accounting for my perspective.
So by centered, did you mean centered on an agent?
Right, yeah.
So next question there, and then the question we have.
Hi, thank you very much for a good presentation of such complex problem like multiverse. I would like to have an explanation about what a molecule of two atoms of hydrogen and one of oxygen, where they have a superposition, one electron of oxygen, and having in two branches, but we are seeing it in real world, not in different world. How you explain that from your perspective?
I'm not sure. Can you repeat the question?
It is in superposition on electron for two atoms of hydrogen in molecule of water which you are drinking now.
Yeah.
It is real world, it's not different world.
Yeah.
How you have an explanation from your perspective?
So if I of course I can observe phenomena of entanglement, and one way to characterize that would be that decoherence with respect to that entangled system has not taken place. So I can have superpositions, I can have entanglement, and I can observe implications of that, effects of that. And of course, actually, those kinds of experiments are carried out, so it is a very real scenario. And however, it's not in contradiction to Everettian quantum mechanics, because Everettian quantum mechanics does nothing else than say once decoherence has happened between those different branches, then those individual branches behave like individual balls, like independent.
Okay. Thank you. One question. We have one more there, and then we have to move on.
Hello, it's not a physics question. Am I responsible for my actions, or can I blame decoherence if something goes wrong?
That's a very good question. Yes. I don't have a full-fledged answer to that. I would argue, however, that those kinds of issues arise in all sorts of in the context of all sorts of physical theories, right? So they arise in deterministic systems where you also say, am I responsible given those unique deterministic evolution of the world? And they probably arise in a fairly similar way in this system, which in a sense is also a deterministic system.
Okay, good. Let's thank Richard again.